Hello there. Thanks for joining us today. I have been looking over your profile, and it seems you have a solid 5 years of experience in the Angular ecosystem, often leading modules and making architectural decisions. To start things off, I'd love to get a general sense of how you view the framework. In your own words, what is the primary purpose of an Angular component, and how does that fit into the way you design a scalable application?
Thanks for having me. I'm glad to be here. From my perspective, the primary purpose of an Angular component is to serve as the basic building block of the user interface. Essentially, a component is a way to encapsulate a specific patch of the screen by combining a logic class, which handles the data and behavior, with an HTML template that defines the presentation. When I'm designing for scalability, I view components as the units of a larger design system. Instead of building massive pages, I break everything down into small, independent, and reusable pieces. This makes the code much easier to maintain and organize. If I can isolate a feature into its own component, I can test it in isolation and ensure that changes to one part of the UI don't accidentally break something completely unrelated. It's all about separation of concerns and creating a modular architecture.
That makes sense. Since you mentioned the connection between the logic and the template, let's talk about how that communication actually happens. Could you explain data binding in Angular?
Sure. Data binding is essentially the bridge that allows the application to communicate between the TypeScript code in the component and the HTML template. It's what ensures that the data the user sees on the screen stays in sync with the actual state of the application. There are a few different types depending on the direction of the data flow. Interpolation and property binding are one way. They send data from the TypeScript logic out to the view. Then you have event binding, which does the opposite, sending data or notifications from the view back to the logic, like when a user clicks a button. Finally, there is two-way binding, where the view and the logic are synchronized in real time. If the user changes a value in an input field, the variable in the code updates automatically and vice versa.
Speaking of that two-way synchronization, a lot of developers use ngModel. Could you clarify the specific difference between using ngModel and standard property binding?
Right. Property binding, which is the syntax where you use square brackets around a property, is a one-way street. It allows you to pass data from your TypeScript code into an HTML element. However, any changes the user makes to that element in the browser will not reflect back in your code. ngModel, on the other hand, implements two-way data binding. It creates a continuous synchronization between the TypeScript variable and the HTML input field. If the variable in the code changes, the input view updates. If the user types something new into the field, the variable in the code updates instantly. It's very powerful for forms, though as a senior developer, I'm always mindful of when to use it versus reactive forms, depending on the complexity of the validation needed.
Let's dive a bit deeper into the internal mechanics. One of the more mysterious parts of Angular for some is Zone.js. What is the concept of Zone.js, and how does it fundamentally enable change detection?
Zone.js is really the engine that lets Angular know when to check for updates. Fundamentally, it is a library that creates a wrapper around all asynchronous operations in the browser. We're talking about things like timers, HTTP requests, and user events like clicks or keyboard inputs. In a standard JavaScript environment, the framework doesn't naturally know when an asynchronous task finishes. Zone.js solves this by patching these browser APIs so it can intercept them. It acts like a notification system. When any asynchronous event completes, Zone.js notifies Angular that something might have changed in the application state. This notification is what triggers the change detection process. Angular then traverses the component tree, checks for data updates, and refreshes the user interface to match the current state of the data. Without Zone.js, we would have to manually tell Angular to check for changes after every single API call or timeout.
That's a great explanation. Now, if we're talking about change detection, we have to talk about performance. In a large-scale app, running that full check every time can be expensive. How do you prevent unnecessary change detection cycles in a component?
The most effective way to handle this is by using the OnPush change detection strategy. By default, Angular uses the default strategy, which means it checks every component in the tree whenever any event happens, regardless of whether that specific component was involved. In a huge application, that's a lot of wasted CPU cycles. With OnPush, I'm essentially telling Angular, only check this component if one of three things happens. First, if one of its input properties changes by reference. Second, if an event originates from within the component itself, like a click. Or third, if I manually trigger a check using changeDetectorRef. This significantly improves performance because it allows Angular to skip entire branches of the component tree. If the inputs haven't changed and nothing happened inside the component, Angular knows it doesn't need to re-render that branch. This is where immutability becomes really important.
You actually just touched on immutability. Could you expand on that? Why is immutability so crucial for state management in Angular?
Immutability is the practice where once an object or array is created, it cannot be changed. Instead of modifying an existing object, you create a brand new copy with the updated values. In Angular, this is critical because of how the OnPush strategy and change detection work. Angular checks for changes by comparing references. If I mutate an object by changing a property inside it, the reference to that object remains the same. If that object is an input to a component using OnPush, Angular will look at the reference, see it hasn't changed, and assume the data is the same. This leads to bugs where the UI doesn't update even though the data has. By using immutable patterns, I'm changing the reference of the object entirely. When Angular performs its check, it sees a new reference and immediately knows that the view needs to be refreshed. It makes the application much more predictable and stable.
I want to shift gears to how you handle data transformation. We use pipes a lot for that. Can you explain the difference between pure and impure pipes?
Definitely. A pure pipe is the default. It only executes when Angular detects a change in the input value itself. This usually means a change in a primitive value, like a string or a number, or a change in an object reference. Because they only run when the input actually changes, they are incredibly efficient and don't run on every change detection cycle. An impure pipe is different. It's triggered every single time Angular performs change detection, regardless of whether the input value changed. You generally only use impure pipes when you need to track internal changes within an object or an array, like adding a new item to a list. Since adding an item to an array doesn't change the array's memory reference, a pure pipe wouldn't trigger. An impure pipe ensures the UI updates, but you have to be very careful with them because they can seriously degrade performance if they contain heavy logic.
Let's talk about architecture and component communication. Imagine a scenario where you have a deeply nested component structure. How do you ensure that an action in a very low-level child component correctly updates a state variable in the root component?
In a professional production environment, you absolutely want to avoid prop drilling. Passing data through 5 or 6 layers of middle components that don't actually need the data just to get it to the root is a maintenance nightmare. The best approach here is a centralized state management strategy. I would typically create a shared service that holds the state using a BehaviorSubject. The low-level child component would inject this service and call a method to update the value. Meanwhile, the root component would subscribe to that same service. This creates a direct communication line between the child and the root. The middle components are completely bypassed, which keeps them lean and decoupled. It makes the data flow predictable and allows any other component in the app to easily tap into that same state if they need to.
You mentioned BehaviorSubject. Since that's part of RxJS and RxJS is central to Angular, could you break down the differences between a subject, a BehaviorSubject, and a ReplaySubject?
Sure, I like to use analogies for these. A standard subject is like a basic radio broadcast. It sends data out to whoever is listening at that exact moment. If you subscribe after a value was emitted, you've missed the boat. You won't get any previous values, you only get what happens from that point forward. A behavior subject is different because it requires an initial value, and it always remembers the very last piece of data emitted. When a new listener joins, they immediately receive that current value. It's perfect for representing state, like a user profile or a theme setting, where you always need to know the current value the moment you load a component. Then you have the ReplaySubject, which is like a DVR. It can be configured to remember a specific number of past values. For example, if I set it to replay the last 5 emissions, any new subscriber will immediately get those 5 most recent values in order, regardless of when they joined. It's very useful for logging or for scenarios where a sequence of events is important for the new subscriber to understand.
Let's move into some more specific implementation details. If you were building a custom directive, how would you ensure it interacts correctly with the host element's DOM structure?
When I'm building a custom directive, the first thing I do is use elementref to get a reference to the DOM element. However, for the actual manipulation, I always use renderer2. Using renderer2 is crucial because it provides a safe abstraction layer. If the application ever needs to run in an environment where the browser DOM isn't available, like during server-side rendering with Angular Universal, direct DOM manipulation via elementref would crash the app. Renderer2 ensures the code is portable and safe. Regarding the lifecycle, I typically perform DOM manipulations within ngOnInit or ngAfterViewInit to make sure the element is fully initialized before I touch it. If the directive needs to react to dynamic data passed in via an input, I implement the ngOnChanges hook. This allows the directive to detect when an input property has been updated, and then use renderer2 to update the styles or attributes of the host element accordingly.
That's a very disciplined approach. While we're on directives, could you clarify the difference between a structural directive and an attribute directive?
The simplest way to distinguish them is by what they do to the DOM. Structural directives change the actual layout of the DOM by adding, removing, or replacing elements. You can always spot them because they are prefixed with an asterisk, like *ngif or ngFor. They essentially decide if an element should even exist in the document. Attribute directives, on the other hand, don't change the structure. They only change the appearance or behavior of an existing element. For example, a directive that changes the background color of an element based on a condition is an attribute directive. The element stays in the DOM, but its attributes or styles are modified.
I want to talk about forms for a moment. Forms can get incredibly complex in enterprise apps. Imagine you have a deeply nested form structure and you need to implement custom cross-field validation logic that requires access to sibling form controls. How would you handle that?
For cross-field validation between siblings, the key is to avoid putting the validator on the individual controls themselves. Instead, you should apply the validator to the common parent form group. Because Angular validators receive the control or group they are attached to as the first argument, a validator placed on the parent group has full access to all its children through the controls. Object. This allows the custom validation function to pull values from 2 different sibling controls, compare them, and then set an error on the group as a whole or even target a specific child control for the error message. To make this scalable and avoid repetitive plumbing in deep nests, I usually create a reusable validator factory. This factory takes the names of the sibling controls as arguments and returns a validator function. That way, if I have the same password and confirm password pattern in multiple places across the app, I can just call the factory and apply it to the relevant group.
That's a solid architectural choice. Switching to dependency injection, could you explain the mechanism of DI providers, specifically the difference between provided in, root, any, and module level scope? Candidate dependency injection is what makes Angular so flexible. Providers are essentially the instructions that tell Angular how to create a service. When we use provided in, root, the service becomes a singleton. There is only one instance of that service shared across the entire application. A huge benefit here is that it's tree-shakeable. If the service is never actually injected anywhere, the Angular compiler will remove it from the final production bundle, which keeps the app lean. If we provide a service at the module level by adding it to the provider's array of an ngModel, that service is available to everything in that module and any child modules. This is less common now with the shift toward standalone components, but it's how you'd traditionally scope a service to a specific feature area. Then there's provided in any. This is an interesting middle ground. Angular creates a new instance of the service for every lazy loaded module that injects it, while still sharing one single instance among all the eager loaded modules. It allows you to maintain separate states for different lazy loaded sections of the app without making the service completely private to just one component. You've mentioned a lot of high-level patterns. I want to touch on component contracts. When dealing with inputs and outputs, how do you prevent an uncontrolled component from accidentally emitting values or receiving unexpected inputs? What patterns do you use to enforce stricter contracts?
This is a common pain point in large teams. To prevent uncontrolled behavior, I move away from using simple primitive inputs. Instead, I prefer using a strict contract pattern, like a configuration interface or a specific input object. This allows me to validate the data before it ever reaches the component logic. To stop unexpected emissions, I implement a guard mechanism inside the component. Before calling an output emitter, I check if the new value is actually different from the current state. This prevents the parent component from being hit with a flood of redundant events that could trigger unnecessary change detection. For even stricter contracts, I lean on the state management or viewModel pattern. In this approach, the component doesn't manage its own state at all. It simply reacts to a single source of truth. I also make heavy use of TypeScript's read-only modifiers and the required property for inputs. By marking an input as required, I ensure that the parent component provides the necessary data at compile time, preventing the component from ever entering an undefined or unstable state.
Let's look at a specific scenario. You have a component that displays data streamed from an HTTP API. If the user navigates away from that page and then returns, how do you ensure the data fetching logic only runs if the component is still mounted? And how do you avoid memory leaks?
This is a classic lifecycle management problem. The goal is to ensure that any active subscriptions are terminated the moment the component is destroyed. The most effective way to do this is by managing the subscription lifecycle using an observable stream. I typically use a subject or a signal and pair it with the takeUntil operator. I'll create a destroy subject that emits once in the ng on destroy hook. By piping my HTTP request through take until this destroy $, the subscription is automatically canceled if the user navigates away before the server responds. Another great way to handle this is by using the async pipe in the template. The async pipe is brilliant because it automatically handles the subscription and unsubscription for you. When the component is removed from the DOM, the async pipe cleans up the subscription. Both of these methods prevent memory leaks and avoid the updating a destroyed component error that happens when a callback tries to execute on a UI state that no longer exists.
Very clean. Now imagine you have a directive and you want that directive to share state or data across multiple elements that the directive is applied to. How would you achieve that?
This is an important distinction to make. You cannot store the shared data inside the directive instance itself, because every single element that the directive is applied to gets its own separate instance of that directive. To share state across multiple elements, I would create a separate service to act as the single source of truth. The directive then injects this service. Since services are singletons by default, any change made by one directive instance to the service's state is immediately available to all other instances of that directive across the application. The directive essentially becomes a thin wrapper that communicates with a centralized state manager.
Let's touch on routing briefly. What method should you use to initiate a navigation change between routes, and are there different options depending on the path?
To trigger a navigation change, I use the router service. Specifically, I call the navigate method. This method is the most common choice because it takes an array of commands and allows you to pass navigation extras, like state or query parameters. It's also very flexible for navigating relative to the current route. If I have an absolute path and I want to go straight to it without worrying about the current route hierarchy, I might use navigate by URL. But for the vast majority of use cases, navigate is the standard because of its flexibility and the way it handles route parameters.
When would you implement a route guard, such as can activate?
I use route guards when I need a security checkpoint that runs before a component is even loaded. The most common use case is authentication. I'll use can activate to check if a user is logged in before allowing them into a private dashboard. Beyond just login, I use guards for permission-based access. For example, ensuring only a user with an admin role can access the settings page. I've also used them to create unsaved changes warnings. In that case, I'd use a guard to check if a form is dirty and warn the user before they navigate away, preventing them from losing their work.
Finally, just to wrap up on the basics, could you tell me what an ngModule typically defines and how it helps in organizing a project?
An ngModule is basically a container that tells Angular how to organize the different pieces of the application. It groups together related components, directives, pipes, and services. Its main job is to define the boundaries of a feature. It specifies which components are available for use within that module, and which external tools or other modules are required for those components to function. By using ngModules, I can keep the code clean and decide which parts of the app should be shared globally, and which should be kept private to a specific feature. While the framework is moving more towards standalone components, understanding the module system is still essential for managing legacy code and organizing large-scale dependency trees.
This has been a very thorough discussion. You've shown a deep understanding of both the low-level mechanics and the high-level architectural patterns of Angular. I appreciate the detailed examples. We'll be in touch soon regarding the next steps.
Thank you very much. It was a pleasure discussing these topics with you. I look forward to hearing from you.